Hello learners, till now we have learned many things about the control system, then the control system modeling, and we have seen that transfer function approach is one of the very important approach for modeling of the control system. But sometimes when the system becomes complex, it becomes difficult to derive the transfer function by just having the differential equation describing the system and then taking their Laplace transform and then rearranging them. So for such cases, there are two methods used for the derivation of the transfer function. First is the block diagram reduction technique, and second is the signal flow graph technique using Mason-Skin formula. Within this lecture, we'll be discussing about the block diagram reduction techniques. So what is a block diagram? We have already said that a block diagram is a drawing that is illustrating the system whose major parts or components are represented by blocks. Everything, like we have already in my previous lectures, you have seen a plant represented by a block G. We have seen a feedback element that is represented by a block H. So you have seen a comparator represented with the help of a particular symbol. So within a block diagram, we are having major part or components replaced by blocks which are joined by lines to display the relationship between the subsequent blocks. So what are the elements of the block diagram? This is first is the functional block that we have shown over here. That is like the block diagram of the system transfer function, block diagram of the feedback link. So this is the function block diagram. Then there can be a summing point like comparator that we have represented with the help of this symbol. So here A is fed as positive, C is fed as negative. Here we can change the sign also. This positive can be changed to negative, negative can be changed to positive. So the output can be varied as per our requirement. Then there is one more element, that is the takeoff point. So we can see A is the input that is being given to the block G1 so as to produce the output B. From A, we have just taken a part of the input that is given to the block G2 so as to produce the output C. So these are three main elements of the block diagram representation. Then once we are having the block diagram representation, sometimes, as we'll see with the help of the example at the last of this video, that the system becomes so tedious that we cannot directly give the value of the transfer function of the system. So for that, we have to use the block diagram reduction rules. So one of the first rule for reducing the block diagram is that in case we are having two blocks which are connected in series, then they can be replaced by a single block that is having the transfer function which is a product of them. Like in this case, XS is given as input to GS, that is producing an output US, which is given as input to G2S, that is producing an output equal to YS. So US can be written as equal to the G1S is the transfer function between XS and US. So US can be taken as equal to G1S multiplied by XS. Similarly, Ys is equal to G2S multiplied by US. So these two equations, this is the first equation, this is the second equation. Then over here, if we substitute the value of US from this equation, then we get Ys is equal to XS into G1S into G2S. It means that in case we are having two blocks which are having particular transfer function and they are connected in series, then the overall transfer function can be obtained by taking the product of the transfer function of the individual block. And sometimes these blocks are connected in parallel. Here we are giving this input. It is producing some certain output. This input is also given to another block that is producing an output equal to Y2S. Then here it is being given to the summer so as to produce the overall output. So these are in the parallel now. So what is Y1S? Y1s is equal to X1s is the input, G1s is the transfer function of this path. So Y1s is equal to Xs multiplied by G1s. Similarly, what is Y2s? Y2s is equal to Xs multiplied by G2s. So that we have written over here. Then what is Ys? Overall transfer function, that is equal to the sum of these two outputs, that is equal to Y1s plus Y2s. So Ys is equal to Y1s plus Y2s. From here, we substitute the value of Y1 here, and from here, we substitute the value of Y2 here. So Ys is coming out to be Xs into G1s plus G2s. It means that when two blocks are connected in parallel, then their overall transfer function is given as the sum or addition of the individual transfer function. So that is the second rule. So first rule, that when the blocks are connected in series, then their transfer function will be multiplied together to get the overall transfer function. When they are connected in parallel, then the overall transfer function can be a sum or difference of the transfer function depending upon the type of the comparator that we are using. Then another thing that we sometimes we are supposed to do is to shift the takeoff point. So like this is the takeoff point over here. It is likely to be shifted to this place. In this case, we can very well see that Ys is being taken from Xs as input and Gs is the transfer function. So Ys is equal to Xs multiplied by Gs, and we are just taking the signal from here, that is equal to Xs. In case I'm just shifting to it to this place, so now the signal will become, at this place the signal will become Xs multiplied by Gs. And if we just want to take up the this signal from here, if we just take this directly, then we'll get the signal as Xs multiplied by Gs. But we cannot change the original system. So if we take up this takeoff point from this place to this place, then we have to add a block that is having a transfer function equal to 1 by Gs. So this is the rule with respect to the shifting of the shifting of the takeoff point in the forward direction. Then shifting of the takeoff point in the reverse direction. Here we are having the takeoff point over here that is giving you a signal that is equal to Xs multiplied by Gs. Now this takeoff point is to be shifted at this point, like this. Here, it is being transformed to this. So when we are changing this takeoff point to this, then at this point the signal is Gs. So if we want to take a complete this signal from the takeoff point, then this is to be multiplied by G. So P will become equal to Xs Gs only in case we just connect a transfer function block over here. So what becomes the rule? The rule is that when a takeoff point is shifted in the forward direction, then we have to, when the takeoff point is shifted in the forward direction, then we have to add a transfer function equal to 1 divided by Gs in the forward path. And when the takeoff point is shifted previous to a block, then we have to add a transfer function Gs in the path of the takeoff point. Then next is the block diagram reduction with respect to the shifting of the summing point. Like we are having a summer present over here, it is to be shifted over here. So if we look at the output that we want to obtain from this particular block diagram, we will see that in case a summer is to be shifted ahead of is after a block, so in that case we have to add a transfer function Gs in the path of the and this is in the path of the summer. So here we have to add a transfer function Gs. This you can check yourself. Only if we are providing a block Gs over here, the overall input that will be getting from the overall output that we are getting from this particular overall block, it will remain the same. So we have to provide a transfer function Gs in the path of the summer. Then similarly, in case we want to move a summer ahead of the block, then we have to add a transfer function 1 by GS in the path of the summer. So only then the output will remain the same as it is. So yeah, these are the block diagram reduction rules, basic, when they are connected in series, when they are connected in parallel. Sometimes we tend to change the position of the takeoff point. Sometimes we want to change the position of the summer. And all those cases we have discussed till now, that in case we are changing the, we are making the summer ahead of a block, then we have to add a transfer function 1 by GS. In case it is to be moved after a block, then we have to add a transfer function GS in the forward path. And similarly, we have derived the rules for the takeoff point to be shifted before a block or after a block. Then there is a very important block diagram reduction rule. In case we are having this closed loop type of the system, we are having such a configuration available, then this overall loop, it can be replaced by the transfer function of the closed loop type of the system, that is GS divided by 1 plus minus GSHS. Here, when we'll take negative and when we'll take positive, that depends upon the type of the feedback. In case negative feedback is provided, then we'll be taking 1 plus GSHS in the denominator. In case there is a positive feedback, then we'll be taking 1 minus GSHS in the denominator. So this is also one of the very important tool that helps in reduction of the block diagram and determination of the overall transfer function of the system. So what are the steps for the block diagram reduction? So first of all, the directly connected blocks in series, they are shifted to the single block by multiplying their overall by their individual transfer function to get the overall transfer function of the series connected block. Then parallelly connected block also connected are just transformed into a single block by taking the single block transfer function as the addition or the subtraction of the individual block transfer function. Then in case we are finding some certain closed loop, so those minor feedback loops can also be replaced by their overall transfer function of the form GS divided by 1 plus minus GS. Then if there is, then we have a look at the overall block diagram, and if shifting helps in shifting of the takeoff point or the shifting of the summing point towards left or right, that is helping in reduction of the block diagram, then that process is done. And these steps are repeated again and again to have a simplified system. Once we are having a simplified system, then we can directly get the value of the overall transfer function of the system. So for that, let us consider this is the first block that we are considering. You can see the complexity of the block diagram. So we cannot directly get the transfer function for this particular block diagram because this block diagram seems to be very complex. So we have to use the block diagram reduction techniques as we have discussed in this lecture. So first step was we will just replace the series connected block by a single block. So G1, G2 and G3, they are connected in series with each other. So they can be replaced by a single block G1, G2, G3. Then we are having the, so it means that this from this particular block diagram, we have simplified it and we have converted it to this. Then parallelly connected block, they are replaced by a single block. So from this block diagram, we shift to this block diagram. So these three blocks can be replaced by a single block, that is G4 plus G5 plus G6. Here also a positive sign is there. So they are, so now you can see that complexity, how we are able to reduce the complexity from this first network. We have just shifted to the third network. Now we can see now the third step is, in case we can observe a simple loop within that is present within the block diagram. So this is the simple loop that we can directly identify, and it can be replaced by overall forward path transfer function is G1, G2, G3, and reverse path transfer function is H0. So in this case, if we get the, and the positive feedback is there. So for this particular loop, the transfer function is G1, G2, G3 divided by this. And this will remain as it is, and H1 feedback will be present here. Now, after this conversion, after this replacement of this particular loop by this overall transfer function, we get two blocks which are coming in series with each other. So overall transfer function of these two blocks will be just obtained by taking the multiplication of the transfer function of these two blocks. So this is the overall transfer function for these two blocks. Then again, we are having a feedback equal to H1. Now we can identify a single loop that is having a forward transfer function that is represented by this. Then we are having a feedback block that is having a transfer function equal to H1, and there is a negative feedback. So just applying the relation for replacement of loop, we can get the value of CS upon RS is equal to this. You can see that within a few steps we'll be able to get the transfer function of a very complex block. So we'll just keep on looking at the system. We'll just keep on reducing the blocks by the application of the rules that we have discussed, and within few steps we'll be able to get the overall transfer function of the system. So that is the way we get the overall transfer function of the system. So transfer function of the system is a very important characteristic of the system, because the roots of the transfer function, they are having a very important role to play within the stability of the system. Like corresponding to a transfer function, we are having a characteristic equation. In case we consider the transfer function, normal transfer function of a closed loop type of the system, that is GS divided by 1 plus GSHS. So within this, the denominator is 1 plus GSHS. If we make up this denominator as equal to 0, then that is called the characteristic equation of the system. And the roots of the characteristic equation of the system, they play a very important role in ascertaining the stability of the system. If all roots of the characteristic equation lie in the left half of the S plane, the system is stable. Otherwise, it is not stable if we are and those particular criteria we'll be studying. So first, over here, I just wanted you to introduce to you to the characteristic equation that is obtained by making the denominator of the transfer function as equal to 0. That is the characteristic equation. And the order of the characteristic equation ascertain the order of the system. Like in case we are having a transfer function represented by S divided by S plus 2. So within the denominator, the equation is of first order. So that will be a first order system. In case we are having a transfer function S divided by S cube plus 3S square plus 4S plus 1. So within the denominator, we are having the third root, the order of the equation is equal to 3. So the order of the system will also become equal to 3. So here we should not get confused with the type and order of the system. In the order of the system is the order of the equation, order of the characteristic equation, means the highest part of highest, what order of the equation we are using. And type of the system simply describes that how many roots of the characteristic equation lie at S equal to 0. So in case we are having a transfer function 1 divided by S into S plus 1. So at S, it is having one particular pole. So it will be a type 1 system. In case the overall transfer function is 1 divided by S square into S plus 1 into S plus 2. So in the denominator, we are having S square term. It means that two roots are lying at S equal to 0. So it means that this is the type 2 system, and so on. So we should not get confused with the type and order of the system. Order is the highest power of S in the characteristic equation, and type is the total number of roots of the characteristic equation lying at S equal to 0. So all these things, they affect the stability of the system largely. So we'll be discussing those things within the upcoming lectures. So thank you so much for the patience hearing. So we'll continue in the next lecture. So I just